When I was in school learning about stars, I was told that they are perfect spheres. And while that is almost correct, they kind of missed one point. Stars can squash. Welcome back to the channel. I'm Seti, a PhD student studying the Milky Way, but today we're going to be scaling it all the way down and focusing something a tad bit smaller. On this channel we cover everything and anything space related, so if that's your cup of tea, hit subscribe to get notified when I post new videos. To understand why stars squish, we need to understand why they spin, and for that story starts all the way back to their birth. Stars form in huge gas clouds, and small pockets of this gas will have relatively high density compared to other parts, and even though it does take a while, eventually that gas does draw closer and closer to each other and collapse down into a star. All the drawn in gas will be coming in at some velocity or angular momentum. Now some of it will cancel out with other pockets of gas, but in general there will be some left over and some net velocity and angular momentum which then gets imparted onto the star. And this will become the star's own angular momentum, which is basically its rotation speed or its spin. The same concept is applied to planets and even black holes. They all operate on the same manner, however, it's just on vastly different mass scales. Jupiter, for example, pulled in a lot more gas than Earth did, and that gas's angular momentum helps spin the gas giant up, so now its day is only about 10 hours. But back to the star. If that leftover angular momentum is really high, then the star will be spinning really fast, and it is in those scenarios that we get the really squashed stars. Let's zoom in on a little bit of plasma in this star. It can be anywhere within the star, but doesn't matter. What matters is that it'll be under a lot of different forces, pressure, magnetic field, centripetal force, and gravity. But the big ones determining where this bit of plasma will be orbiting are the last two, the centripetal force and gravity. The centripetal force has to do with the orbit of the star, and it has the formula F equals mv squared over r. It kind of looks like the kinetic energy equation, somewhat similar mechanics are going on here. If we moved our plasma further away, the formula tells us that in order to keep that force the same, we need to start increasing its orbital speed, so it will need to move much faster. Now let's consider the gravitational force. This has all to do with the mutual pull of this little bit of plasma and the rest of the plasma that's orbiting within that orbit. We don't need to consider anything beyond the orbit of this little pocket of plasma. This all actually cancels out, so we don't need to worry about it. The gravitational force is given by the formula F equals g big M little m over r squared. So if you move the plasma closer and closer, the force increases, but that also depends on how much mass there is within the orbit, and that can change if you pull it closer or push it away. In a perfectly spherical star, centripetal force and gravity balance perfectly. We can do this with the maths. So here the total force is equal to 0, they balance perfectly, so g big M little m over r squared is equal to little m v squared over r. We can get rid of the little m's and one of the r's on each side, so that we're left with g big M over r is equal to v squared. So the velocity of that little bit of plasma is proportional to the mass enclosed within the orbit over its distance. Fast rotating stars have a much higher centripetal force at the equator than they do at the poles, so already we're not off to a good start in this scenario. Even if the star is rotating almost solidly or rigidly in this case, the plasma at the poles may have the same rotational velocity or angular velocity. This will be in like degrees per day or something along those lines. So it might move at the same amount of degrees per day, but its tangential velocity, and this is going to be in meters per second or kilometers per hour or something like that, will be much higher at the equator. This means that the centripetal velocity is slightly higher overall near the equator, so if the velocity is then high, then in order to restore balance between the centripetal force and the gravitational force, it'll need to orbit slightly further away. Also, the plasma at the poles will have a much lower tangential velocity, so they don't experience as much centripetal force in those areas. So gravity wins just by a little smidge, and thus the plasma will need to orbit just a tiny bit closer in order to balance those forces there. So altogether you have plasma at the poles just squishing down a little bit, but then they're stretching out at the equator, creating a very squashed, or what we would call an oblate star. Now, of course, there is a lot more that goes into keeping a star alive. You have a couple other forces, such as those from the magnetic field, fluid dynamics and pressure and, heat and all that to consider. So it isn't as simple as this, it's a little bit more complex, but it is kind of remarkable how just the spin of the star could really change its shape and, how the plasma orbits. It's quite amazing. Now let's have a look at some notable squashed stars. Some of these you can actually observe in the night sky. Vega is the 6th brightest star in the sky. It's got a magnitude of around about 0.03, so quite bright, but it is not the most spherical. The radius of Vega is about 19% larger at the equator than it is at the poles, and it is rotating at the surface. It is rotating almost fast enough to get pulled apart, but not quite. Altair is not as bright as Vega, but it certainly still is quite bright. It is the 13th brightest star within the northern hemisphere, and it also forms the summer triangle along with Vega, so that's quite interesting. It rotates in around about 9 days, which is staggeringly fast compared to especially the Sun. The Sun rotates differently at different speeds around the equator than at the poles, but both altogether it takes around 26 to 36 days to make one full 360 revolutions, so much faster for sure. Altair is one of the few stars we have direct images of. Its equatorial radius, so the radius at the equator, is 25% larger than at the poles, which is very, very big. That's around about 40% of the Sun's radius just added on to the equator. I've left the best star till last. Achernar is the 10th brightest star in the night sky. It is definitely visible to the naked eye, so you can go out and view it. It's the primary star of a binary system with a white dwarf, which is really unique and very interesting. Achernar is the least spherical star we've observed so far in the Milky Way. The radius at the equator is actually a whopping 56% larger than at the poles. It is on the verge of spinning apart. If it span any faster, it would just fly apart, which is wild and so cool. I used to think stars had to be spherical because of gravity, but I am yet again just shown how amazing physics can be. Thank you very much for joining me while I discuss one of the weirdest aspects of space and astronomy. I hope you learnt something new today, and hopefully maybe you've got some targets to view in the night sky as well. Thank you very much for joining me, and I shall see you in the next video. Don't forget to subscribe.